Hey guys, welcome. I'll explain about my design here. I won't go over too much about the details and everything, how the processor needs to work and how it's built. I'll more go over the code and the specific points I found that needs to be clarified, especially things that I added that's not in the original design. And when I mean the original design, I talk about the book Digital Design and Computer Architecture RiscV edition by Sarah Louise Harris, L. Harris, and David Harris. It's a great book. If you want to understand my design fully, if you want to understand any RiscV design fully, I recommend this book. And so, again, I won't go over how RiscV processor work, but only specific points. Okay. Hope you enjoy, and if you have any questions, feel free to ask. I'll gladly answer them. Okay, so let's start. Yes, so why we need the branch control? Let's start with that. The branch control is here. This is the unit of the branch control. And it gives me a PC source signal that tells me if I need to branch or not. Okay. Okay, so before in the original design, they did branch greater equal. Okay, this operation, this instruction, and they didn't have the branch control. They didn't need it. It works fine. Okay, but if we add the branch less than simultaneously with the branch greater equal, we need it. The reason is we do the same operation in the ALU to calculate if we need to branch at the branch greater equal and branch less than. We do this operation, okay, set less than, which if one operand is greater than the other, it sets the result as 1, otherwise the result is 0, and obviously the 0 signal is adjusted accordingly. Okay, the problem arrives because we need the 0 signal to always be 1 if we want to branch. Okay, we always want the 0 signal to be 1. Why is that? Because we have here PC source E, we design it in such a way that the enable branch needs to be 1 and the branch E needs to be 1. Branch E will always be 1 for any branching instruction. This is just the default if it's branching instructions, so we make it 1. And enable branch, well, it depends if the branch is actually needed. Okay, so for example, if source A is not greater than source B, so maybe we don't want to jump. Okay, we don't want to branch, so we don't always want to branch, only based on the specific operands. But again, we do the same operation from branch less than and branch greater equal. Okay, so we need to differentiate them. So we want to branch for the instruction branch less than if 0 signal will be 0, and for branch greater equal if the 0 signal will be 1. Okay, that's the point of the branch control. Okay, so about the register file, the first thing I want to note is the first register x0 is always 0. So no matter what, if your address is 0, you will read 0. Okay. The second thing is, I want you to notice the negage clock. It's used for writing. We write only on negage. The reason is after the data is ready, the posage of clock on read data W, we want to write it on the same cycle, on the same write back cycle to the register file. So we do it on the negage. That's I think a clever design by the book. I was curious if we can do it in other way, like maybe add another pipeline stage, or yeah, because that's the only thing I can come up with, because we don't want to forward the data from the read data memory output. That's kind of beating the purpose of the pipelining. But if you know another solution, I would really like to know, and please tell me. Okay, about the forwarding unit, I want to note there's a priority to which stage we will forward. Okay, let's see. So a quick reminder, what is forwarding? Forwarding is if we need to use, for example, a register, like register x1, x2, for example, but it's not yet calculated, right? For example, the register destination, right? The operand destination will be x2 here in the memory stage, and the ALU result will contain the result for it, the data, okay? And we need to use the data of this register already in the execution stage, even though, you know, it's not yet written in the register file. So what we do, we forward it. Yeah, we have the data already ready. So if you see here, we forward it to the execution stage. Okay. So that's what forwarding is, and we can in this design we forward from the memory stage and the write back stage. So now we have a dilemma we need to tackle. Which forwarding takes priority, from the memory stage or from the read data stage, from the write back stage? So because we forwarded we need to choose which result to forward. So the quick answer is we have priority to the memory stage first, and if we don't need to forward from the memory stage, we will forward from the write back stage. So that's the quick answer. The reason for this, and I'll try to be clear, but if you don't understand this explanation, please ask me in the comments. The reason we take the memory stage takes priority in forwarding, because we already okay, so in the scenario the register destination is equal both in the memory stage and the write back stage. What it means that the ALU result M is calculated based on the read data W, but imagine we take it like 2 cycles ago, or 1 cycle ago. We take it 1 cycle ago when read data W was the ALU result M, and the ALU result M was what was coming out of the ALU. So we calculated the ALU result M based on the read data W, right? So this is the updated operand we need to put into the register destination, right? So that's why it takes priority. Hope that's clear. Okay, so now I'll go over the memory unit. This is something I added that is not present in the original design. So I added an option for store instruction like store half byte and store byte, and also load for loading instruction like load byte, load half byte, and also load unsigned. Okay, so how does it work? Let's go over the store extension first. So the store data gives us the data from the CPU that we want to store, for example, and function 3 gives us the type of operation we want to do for store byte or store half byte or store a whole byte, right? So if we want to store a byte, we want to store the first byte here. If we want to store a half byte, we want to store the first half. Okay. Okay. Now, where do we want to store them? Okay. That's what we define by the address, by the two least significant bits of the address. That define where inside the word in the memory we want to store them. Okay, because the word in the memory has 4 bytes, right? So if we want to store 1 byte, we need to replace another byte. Okay, and which of these 4 bytes? So again, the address, the two least significant bits of the address is what defines that. So how does it define that? We input it into the store extension, and based on that we get a W mask. Okay, and the W mask basically just tells the main memory which place inside the word, which byte inside the word is needed to be replaced. Okay, now the memW data has the byte or the half word that we want to save in the place corresponding to the bytes, to the bits, to the bytes we want to replace inside the main memory. So if we want to replace the 4th byte, only the 4th byte, so we will have the first byte of store data be ready as the 4th byte inside the memW data. Okay, we shift the store data, the byte in the store data, number of places based on where we want to save it. So that's how the store extension is implemented. And in the code, you can see the function 3 chooses it, the type of operation we want to do, if you want to save a byte or to save a half byte. The W mask is again chosen. How do we build the W mask? If you want to save a byte, so we need the byte mask will be with only 1 byte, with only 1 bit as 1, and if we want to save half word, we will have 2 bits that are 1. Okay, and as I said, we have 4 bytes in a word, right? So we have the W mask is 4 bits. Okay, and again about memW data, this is important. We want to shift the data. Okay, so if we want to save a byte, we want to shift the first byte. based on where the W mask will is 1. Okay, so if the W mask is 1 at byte 0, so we won't move it. Okay, we will leave it as is because address to LSB will be 0 0. You see, 0 0 0 0. And if we want to save it in the third byte, so W mask is here is 1, and we need to shift it 3 times, so it will be the last byte. Now the way the memory works, the address, we take it, so it will be word addressable, right? So the two least significant bits will be 0 0, because we want to address a specific byte, a specific word, okay, inside the memory. So we get the RAM block and the address, okay. The address, again, we address to a specific word, and here we address to a specific byte, okay. The way it works is column width will be 8, okay. That's the byte size, 8 bits. Okay, now look here, WEA is the W mask, okay. It will go over 4 times, number of columns 4 times, and each time we will check if where is the W mask is 1, okay. If it will be 1, we will enable the memory inside the RAM block, inside the memory itself, to be changed, okay. And if not, if WEA, if the W mask will be 0, we won't change the thing, and we leave the byte inside the memory as it is, okay. So so we address to a specific word, and then I column width will be, for example, I take we start with 0, right? WEA I will be 0, so it will be 0 plus 8, okay. So from 0 to 8, if we want, if we got an enable, we write the data inside the word that was sent to us, the DIN, also from bits 0 to 8, okay. And we do it so on until, for example, we get to 23 to 31, right? And we write it to from 23 to 31 if we have an enable, right? This will be when I will be 3, okay. So that's how the memory write works. And about the read, we just read it, we read it, we read words, okay. I'll explain you next how we can read specific bytes from the memory using the load extension. Okay, so how is the load extension works is we get again function 3 that chooses if we want to read a byte or a half word or a word, and we read a specific byte or a half word from the RAM R data, and we place it as the first byte or the first half word in the load data, okay. After we place it, we sign extend. If it's, for example, if it's a regular load byte, okay, so we sign extend it with the most significant bit, okay. So if the most significant bit is 1, so, and we loaded a byte, so the first 8 bits will be the byte data, and the rest the rest of the word will be filled with ones, okay, because we sign extend, or 0. But if it's load byte unsigned LBU, so it will be loaded, the rest of the word will be loaded with zeros, okay. So that's how the load extension work. Again, if you can see the address, we send the two least significant bits to the load extension, and this is how we choose which byte, for example, or which half word from the memory we want to save inside the load data. Okay, so that's the code for the load extension. Here we choose, again, as previously, which operation we want to do, if we want to load a byte or load a half a word. And the extend type is if we want to make the word that we load signed or unsigned, okay? So address to LSB, okay? Address to LSB is the two least significant bits of the address, right? So with bit 1 of the address to LSB, we choose which half data we want to save, okay? So if it's 1, we choose the second half of the read data, and the read data, again, it's the input from the memory, okay? It's the word from the memory. So we choose if we want to store the first half of the word, which is here, or the second half, okay? Byte data is dependent on both of the address to LSB, okay? We need both bits to select which byte we want to save. I only use byte 0 here because I implement, because I already use the logic I made for half data, okay? So let's take an example to make it clearer. Say we need to load byte, the last byte 3. So that the two least significant bits of the address will be 1 1, okay? It will be 1 1, and so half data will take the second part of the word, right? Bits 31 to 16. Now byte data, okay, will take also the second part of half data, right? Because half data is 16 bits long, okay? So we take the second part of the half data, which contains the second half of the word from the memory. So basically what we did, we took the last byte, right? So that's how it works. And here we extend. It's used for extending the word. If we got a byte, so we need to extend 24 bits. So we extend 24 bits and we put the byte data that we calculated, and we send all of this to load word, which is the output, okay? And load word goes to the CPU. Yeah, and if we don't need to load a byte or a half byte or a half word, so we just send the entire word as is from the memory. Hope that's clear. Yeah, that was the end of the explanation and the end of the video. I hope it was helpful. If you want more explanation about another module inside the processor, or any other thing, any clarification, please ask me in the comments. I will try to help and answer you. Yeah, so have a good day.